Sì, sì, registriamo.
Okay. Let us start. Okay. Okay, so good morning. I want to repeat quickly what we did yesterday. So we had focusing on technical details, leaving the repetition of the how to say methodological discussion to your re-hearing and re-following my yesterday's lecture. Okay, so while integrating by parts, the expression for the virtual work in second gradient materials, in a certain moment we had this term in our expression. This is the projection along the tangent plane of the of every vector, the tangent plane to the boundary C star. This capital SIB is related to the derivative with respect to of W, deformation energy, with respect to the deformation measures. Okay, and we remarked after some considerations that this is exactly this one in the second red square. This is exactly the divergence operator to be used in the surface integration by parts. Okay, now we discussed which kind of surfaces we are considering. So I made this drawing, and then in our okay, I will repeat because Alessandro was not here before. I think that we should write a paper showing the historical development and giving some insights in what we are doing. So this kind of drawing, Erden, we should make better. I am not very good in making this kind of drawings. Okay, so you should consider my lectures as a draft of this paper. Okay, so we'll share the job, and maybe I will have some presentations for future courses. So these drawings will not be handmade, and as you have seen, my drawing is horrible. So you must have a lot of imagination. So try to imagine this body. Okay, this is not with straight lines. Okay, so you have this body, which we called C star here. Then the boundary of C star is made of faces, edges, and wedges. Okay, one face, this is another face, F3. No, sorry, maybe this is F1. No, F3. Okay, this F1 here is disturbing. Okay, then this is F1, this is F2, you have F4, F5, okay? Then how do we define one face? We define one face as a regular surface with border or with boundary. There is not a unique nomenclature in the mathematical literature. The border of F1 is the union of this curve here, this curve, and that curve. Okay, so one face has as a border a set of regular curves, and you have wedges, which are the points in which curves meet and in which you have a jump of the tangent vector to the curve. For instance, here, the tangent vector to gamma is this one, and the tangent vector to the other gamma is that one. Okay? So while the border of a phase can be regarded as a C0 curve, a continuous curve, however, it is the union of C1 curves with a finite number of discontinuity points. Okay? And so we can say that the boundary of C star is equal to the union of a finite number of phases, the union of a finite number of C1 curves, and union of a finite number of points, which are edges. Okay? Now, this geometry is rather simple because this is the geometry of classical Greek volumes, you know. But formally, we need to be very specific because we need all geometrical ingredients of this geometry here for our mechanical considerations. Okay. Then we said that we applied divergence theorem to C star. Okay. And we transformed the divergence of something in the volume into the flux of the same something through the boundary of C star. Okay. Now, remark this. This is very important in our consideration. This is a surface. So this is an integral over surface area. Okay. So we transform a volume integral into an area integral. Okay. So what happens on these curves and in these points is not affecting this surface integral. So divergence theorem is true even if the surface is constituted by a finite number of regular surfaces. A regular surface is, in our context, a surface in which you can define a normal. So it is very trendy in these days to talk about fractal surfaces where you don't have normal anywhere. Okay, so you can define a normal, a tangent plane, which is the set of vectors orthogonal to the normal. So defining a normal in one point is equivalent to defining a tangent plane in that point. And these normals are varying continuously on the surface. So when you reach the boundary of the surface, okay, which are these curves or these points here, okay, you have a limit of the normal. So it is well defined on this edge here. It is well defined the limit coming from F1 side of the curve of the normal. Okay. To understand the geometry. This is a drawing here. Imagine to have a planar cut. I don't dare to draw a plane in the already chaotic drawing which I made, okay? So imagine to have a cut, and this is, okay, I draw, this is the intersection of the plane which I'm drawing here, and you have F1 and F2 cut. So you have, this is the intersection of our plane with the F1 face. This is N1, this is N2. When you move until here, you have a limit of N1, the same from N2, and remark that nu2 and nu1, which are the normal tangent vectors to the border of the face. Nu1 is the normal vector to the face of, to the curve, which is border of F1 here, okay? And nu2 is the same for the face F2. These news appear in the divergence theorem, which we discussed yesterday. Okay. Remark that in general, nu1, nu2 are not N1 and N2. This happens only when this angle is pi over 2. Okay. So in a edge, you have 5 vectors characterizing the geometry in one point of a edge. The tangent vector to the edge, the two limits N1 and N2 of the faces concurring in that point of the edge. Then you have nu1 and nu2, the outer pointing tangent normal vectors to the edge. Okay, so this geometry is not simple, but it can be understood by anybody who studied some Euclidean geometry. And as I said in my class about history of science, only recently in Italy, somebody invented the strange rule that you can study in high school without studying. You can be a student in high school without studying Euclidean geometry. This worked for several thousand years, and then somebody clever, okay, but you are, you belong to a generation who studied this geometry. Okay, so we have on this boundary here this integral to be considered. And I repeat, as volume divergence theorem involves only surface integrals, what happens on the edges and on the wedges for these 3D divergence theorem is not important. Why? Because curves have area 0. So what happens on the curves is not seen by a surface integral. Okay. However, now what we do? We want to apply divergence theorem on the surface. Okay. And divergence theorem on the surface requires regularity of the normals. So you cannot apply divergence theorem to the whole boundary of C star. because in the reasonings which we have done, you know, building these lines starting from the surface. Okay, so maybe it is worth that I repeat in this corner here a little bit the reasoning. Okay, the reasoning which we applied was the following. This is M, the surface, surface where we want to prove divergence theorem. Then we build the translated surface. If this is n, small n, the normal of M, we translate epsilon along the normal M. And we consider V epsilon as the union with H belonging from 0 to epsilon of M HN. The translated along the normal of the amount H of the surface M. Now, if you have here another normal, okay, and you try to apply this reasoning, you will have an empty corner. So you will not have a volume to which you can apply the divergence theorem. Because if you translate here, you see all these corners, all this part of volume will be empty. You do not know how to translate the points in the curve gamma. You can translate following n on one side, if we call this n plus, and this is n minus. Maybe we can zoom this. This is the point representing the curve. This is n minus, and this is n plus. Okay, you translate your surface and you get the slice there. You translate the surface and you get the slice there. This point cannot generate by translation this volume. Okay, so you have a serious problem in generalizing divergence theorem with the methods which I explain you to the case of surfaces which are piecewise regular. So you have a problem where you have a curve on which normals are jumping. Okay, so we split the surface integral into the sum on all the faces of this integral. Additivity of integral gives you the equality. Okay, now you can apply divergence theorem for each integral on each face. This one. Okay, so the delicate point in our process of integration by parts, and this delicate point has been misunderstood in the last 150 years, notwithstanding the fact that Piola did his job in explaining us the difficulties in this context. Okay, the difficulty which now we must face is that after the first integration by parts, we have a surface integral. Okay, this surface integral can be split, let us say, must be split into integrals on each face in order to apply divergence theorem on a surface. Okay? So we can apply divergence theorem only for each of these faces here, F alpha. Okay? Now, we need another technical trick. Here we have PBC d over dxc. So this is what we have seen is important in our integration by parts on the surface. Okay? However, SIB, I want to underline also this for you. Somebody, and he will be correct, will tell me, okay, this is a tensor. It is one time contravariant and one time covariant. Okay? And I agree about this. Okay? However, in our integration by parts, this is an Eulerian index which is saturated with this Eulerian index. And the derivative here is in capital X. So this is a Lagrangian derivative. So from the point of view of our integration by parts, this is a vector. Okay? Because this index is not involved in the differential geometry of the Lagrangian description. Okay? So this can be considered for every I as a vector, and we don't mind in these geometrical considerations about the geometry of the Eulerian description. Okay? This vector here is not a priori tangent. And in order to apply divergence theorem on the surface, we need a tangent vector here. But this is not a problem because we can split PCB into PBD, PDC, because P square is always equal to P. It is a projector. Okay? So we can write this integral on a face. We can write this in this form. We have an S parallel here, and we have the divergence operator there. Okay? Now, we are ready to apply the standard technique of integration by parts. How we do this? This is S parallel here. Then we write d over dx c delta ki there. We place these brackets to isolate the term which we want to integrate by parts, and we keep this p on the right side. And then what we do? D over dxc of the product of this term times this term, it is equal to Leibniz rule to the derivative of delta ki times S parallel not derived plus the derivative of S parallel here times delta ki not derived. So this is equal to that. And this is the standard stuff. And you have this PD. Okay. Okay. Now, I don't know what is happening here. There was a bad cutting and pasting, probably. So I did some terrible mess yesterday. Okay, so you know what? I erase and I repeat another time this reasoning. Okay. So now, what we have? We have two terms. Okay. We have this 2, which is here on the left. Okay, maybe it is better if I do it here. Okay, this is PCD, which is here, d over dx c of the whole. Okay, and then I have this addend 1 here, which is integral over FA, F alpha of minus d over dx c s BIP dB delta Ki PCD. Okay? And this is the area. And this is 1. Okay. Now, let us check what we are doing with 1. 1 is a revolutionary term. Maybe it is not revolutionary. It is a totally new term. Okay? Look what it is. You have integral on a surface of a density of something times delta Ki. And this integral is a work, an energy. Okay? So, what we have in this box here is a surface force, because the integral of this quantity in the blue box, after having multiplied it times a virtual displacement, gives you an energy. Okay? So we could be happy, because if we believe in balance of force and balance of momenta, we could be, okay, we have recognized that also in second gradient materials, we have a contact force per unit area. This is a new one. We already met several terms which are contact forces per unit area. However, a close inquiry about how this expression is made of will teach us that this is not a Cauchy type contact surface. So this quantity is an energy. Okay? Let us look at this. It is a force per unit area. And this is a term which did not exist in first gradient continua. However, it has a novel structure. So here I remind you, Erden we must write this carefully. Okay, so we will discuss with Alessandro and even how to do it. In standard first gradient continua, which you should have studied more or less all of you, we have that surface force is a tensor applied to the normal dot the virtual displacement. Okay, and Cauchy called a postulate the fact that so-called Cauchy vector, which is this one, depends only on the normal. Okay? Okay, yesterday I made a debate about what is a postulate. I want to jump it now. Okay? Let us look to this force per unit area which we have now, whose expression is given by this formula. Now, please remember that P, the projection in the tangent plane, plus Q, the projector in the normal direction, is equal to identity. Okay? Why? Because we have a surface. Okay? We have the normal to the surface. And every vector can be decomposed in a unique way. How? With the decomposition along, okay, this drawing is without perspective, so I will try to do it in a better way. So we have this component here. So we have this vector V, okay? This vector has a normal component along N and a tangent component along, we must do this way. More or less, okay? So P, if this is V, this is PV, and this is QV. And clearly V is equal to PV plus QV. Okay? So we have this property. Therefore, P is equal to identity minus Q. With a component representation, we have that PdB is delta dB minus ND NB. Okay? So what we have to do, we replace this P as written in this representation there. And we make some calculations. Okay? These calculations are made in this way. You have d over dxc of SBI times this coefficient. Okay? You multiply S times delta and S times the normal. Then you apply the additivity of derivative. So you get this addend. Okay. And you have this addend here. Delta goes out. It is a constant. So you have the divergence of SIB along the surface. Okay. And you have SIB d over dx capital C and d and b, the projection. Okay. Now, dx c n d times nbp. Okay? Then you have also nd times d over dx c nb pcd, but pcd saturated with nd is 0 because n projected on the plane is 0. So this term reduces only, this term here reduces only to this term on the box. Okay? What do you get? You get that surface contact force depends on the gradient of the normal to the surface. What is this animal? It is what is called curvature of the surface. Okay? Think about this equality. If you have nd equal 1, this is the definition of unit normal. Okay? The normal has length 1. You calculate the derivative with respect to xc of this quantity. It is 0. So what you get? You get that the gradient of the normal is orthogonal to the normal. The gradient of the normal, if you make this drawing, is very easy. The gradient of the normal is tangent to the surface. Okay? And of course, this concept has been introduced by Gauss. This is the curvature of the face of your, which is part of your contact surface. So what we have in second gradient continua, contact forces, contact surface forces depend on the curvature of the surface. And this is against the dogma of Trussell. Trussell has been a scientist of the past century who claimed that every contact surface force must depend only on the normal of the Cauchy curve. Okay. Now, I will tell another time, but this is a very important subject. I will tell another time that the reasons why one should never call Cauchy postulate the assumption made by Cauchy about contact forces. Okay? This is the statement by Cauchy. Contact force depend only on the contact normal of the surface. Okay. I claim that this is a constitutive assumption. So it is not a postulate. It is a constitutive assumption. Okay? Because the word postulate, we limit, we dedicate, we use only when formulating general statements which are universally valid. And then yesterday I wanted to give an example, a classical example of postulate which everybody has heard. Okay, if you define inertial observer or inertial system of reference as an observer such that every observed material particle which is free, means it is not interacting with anything else in the universe, moves with a rectilinear uniform motion. This is a definition, so it is not yet a postulate. However, the postulate is there exists an inertial observer. This is a postulate. We are talking about every particle, and we say that at least one observer in the universe sees all particles which are free to move in a uniform rectilinear motion. Okay? We cannot call, okay, of course, we should talk, but this is not now the moment, about the nature of a postulate. A postulate cannot be proven experimentally. It is a conjecture. We accept it until some of the consequences related to that postulate and the other postulates we are using is falsified by one experiment. Okay, so if I have a theory which forecasts something which is a specific thing which is not verified experimentally, then we must change our set of postulates. Okay? But in any case, a postulate is assumed to be universally valid in a certain specific set, of course. So, so-called Cauchy postulate is valid only for a specific class of materials. Those materials that can be described by using a particular deformation energy. This one. Okay? So it can happen, and Erden, Ivan, and Alessandro know it very well, that my research in the last years is dedicated to find one example of material for which this deformation energy is not suitable. It can happen when you have a complex microstructure for your material. It can happen that your deformation energy has this form. Okay? Then contact forces depend also on the surface curvature. And what is astonishing, and you should think about this, what is astonishing, that this was already known, written in a book written by Piola in 1848. And if you go to Google, you discover that Google digitalized a copy of Piola's book, of course, written in Italian. And this Piola book was in the library of Wisconsin University. So this book was everywhere, in every library. And I know also why. Piola was a rather rich man. He, you know, for me, I needed to fight all my life for getting a chair in an Italian university. Okay, before being professor in L'Aquila, I was professor in Napoli, I was professor in Rome. Okay, it is very difficult for me to conceive that Piola declined 3 offers of a university chair in Rome, in Bologna, and in Pavia. The reason is that he was the feudal lord of 2 castles, and he had to work nearly half time looking after the family's properties. Okay, so he had no time to go to Rome to be full professor. Okay, but on another side, he was rich enough to have in his palace a lecture room, and he invited many students from Pavia University to follow his private lectures. Okay? And he had money enough to print several thousands copies of his book and to send it everywhere in the world. So that contact forces depend also on surface curvature was known already in 1848. But many people did not want to see it. Okay, and they believed that a particular case was the most general one. To my knowledge, these are the only big scientists in the last century who wrote openly that Cauchy-Truesdell ideas were wrong. Tubin was a student of Truesdell, and he was kicked off the academia and became director of IBM research department. Think about our hard disks before SSD, the hard disks where you have a moving part while writing. This is a patent by Tubin. Okay? And he wrote a paper about second gradient materials. Midlin, another American, he started a violent controversy with Truesdell, and he even wrote a third gradient continuum theory. Paul Germain, who was secrétaire perpétuel of the French Academy of Science, and Sedov, who was the big boss of atomic program in Soviet Union. All these knew that contact forces depend also on surface curvature. However, in every book in engineering schools, you find that this is not possible. Also in science, propaganda, transmitting fake news is very strong. Okay? Trump, yesterday, the great electors of the United States elected Biden, and Trump still is claiming that this is not true. Okay, so you should not believe that the social dynamics which is observed in politics, in the relationship with your girlfriend or boyfriend, and in human relationships is not valid also when we are talking about science. Okay, so the integration by parts, which I have shown you, clearly indicates that there is no chance contact surface force depend also on the surface curvature. Okay? Okay. What do we do with the remaining addend, which we called 2? Okay? With the remaining addend, by the way, you cannot have, this is an a posteriori consideration. Imagine to have this surface, okay? Then you make a small correction and you have this surface. This radius of curvature becomes smaller, okay? Then you make another correction and you make it with a corner, okay? So if contact force depends linearly on curvature, here curvature tends to infinity. So if you have contact force depending on curvature, then you must expect edge forces as a limit of extremely curved surfaces. Okay? But if you don't have the principle of virtual work driving you, you must invent strange reasonings with limiting surfaces for producing edges. Instead, if you have the unifying principle of virtual work, naturally, for every face, you have integral on the face f alpha of d over dxc of this animal here, pcd. And you can apply the divergence theorem on the surface. Now, let us look at a very standard parallelepiped. You have F1, F2, F3, F4, F5, and F6. Okay? So, let us focus, for instance, on F1, which is this one. Okay. The outer normal pointing is this one, and you can move in this direction around using the right-hand rule. So you can orientate the boundary of F1, which is the union of these curves, in a coherent way with the outer pointing normal N1. So you have that these are the tangent vectors, okay, of the curves. This curve is both the boundary of F1 and the boundary of F5, okay, which is this one. So when I apply divergence theorem to F1 and when I apply this integral to F5, I have that this curve is occurring two times, one from one side and the other from the other side. So when I transform this integral on the surface into an integral on the boundary of the face, this boundary is made of gamma 1 union gamma 2 union gamma 3 union gamma 4 alpha. In this drawing, in this particular system body, each face has exactly 4 regular curves as boundary. Okay. Okay. Then in this integration by parts, for the same curve having vector tangent vector t or minus t, depending on the orientation, regarded as a part of the boundary of phase 1 or a part of the boundary of phase 5, you have these two terms appearing. So you have S1BI P1DB nu 1D and S5BI P5DB nu 5D. Okay? Delta key is assumed to be continuous, so it is the same for both sides. Okay, and I repeat here the drawing which we have done several times. Nu 1, nu 5, N1, N5, and also P1 is equal to the identity minus Q1. So component-wise, P1 dB is delta dB minus N1 d N1B. Okay? So you have different fields on both sides. So at the end, you have that the integral over gamma, a unique integral, because gamma is the same, with these two addends, is dual of delta Ki. So the principal virtual work automatically gives you that we have a line integral representing an energy obtained with the inner product of a quantity, is a density per unit line, times a virtual displacement. So because of dimensions, this quantity is a force per unit line. Okay? So the principle of virtual work implies there is a force per unit line as contact force. Okay. So we can have on the edges of a body contact forces per unit line. And this is totally new. Okay. Now, Erdem, we should, in our presentation, underline how this is conflicting with Cauchy approach. Because as you remember, what is doing Cauchy? As he does not know very well the mathematics of the functionals, okay, among the many contributions of Cauchy to science, there are very few ideas of functional analysis. Cauchy, instead of postulating the principle of virtual work or the principle of minimum of energy, wanted to postulate two things: balance of forces and balance of moment of forces. Okay? Now, consider that we are basing mechanics on one postulate, the principle of virtual work, only one. And we deduce everything out of this principle. Okay? Instead, Cauchy needs at least two independent postulates. By the way, one will observe that he adds also other postulates. Okay? So-called Cauchy postulate. Then when he has written stress, he needs to postulate the existence of objective constitutive equations for stress. Then he has to add entropy inequality for selecting among physically feasible constitutive equations and physically unfeasible constitutive equations, and so on. So we have an immediate criterion for telling that Cauchy approach is not the best one, and it is the Occam razor. When you have two, even if they are equivalent, when you have two equivalent postulate schemes, you must prefer the simplest one. However, what is doing Cauchy, and this shows how dangerous is this approach. Cauchy postulates some necessary conditions for equilibrium, necessary in the principle of virtual work postulation, of course, as proven by Piola. Okay? So the question is it always true the vice versa? I mean, these necessary conditions are also sufficient? So in other words, balance of forces and moment of force is sufficient to the principle of virtual work? The answer, only this is true, only for first gradient continuum. So if you invent a postulation for mechanics in which balance of force and balance of moment of forces is the only postulate, then you limit yourself to first gradient continuum. So you cannot see anything else outside. Okay, Erden, what we must write, I will give you something which I've written in Italian, but you must learn Italian, so this will be another exam for you, okay? But everybody has seen, maybe only our mathematician there has never seen it. This drawing is written in every engineering book in continuum mechanics. Cauchy postulates that the contact force on this face of a tetrahedron having normal n depends on the normal n only. This is Cauchy so-called postulate. Okay, so in Cauchy postulates, if you have this surface or if you have this surface, they both have the same normal here. The force Tn per unit area, this is called Cauchy vector. The force per unit area, instead of depending only on the surface, so you have sigma 1, sigma 2, so this is T sigma depending on the surface. Okay, Cauchy assumes that this depends only on the normal. Erden, don't believe to null theorem. He claims to prove that T depends only on the normal. Why? Because null theorem is based on considering this volume and writing the balance of force in this volume. You have edges there. And null assumes no edge forces. So actually, null theorem says when you don't have edge forces, then contact surface depends only on the normal of the surface. Okay? And is misunderstanding what is proving. And I expect from you that we write this in this paper. We must plan. We are planning. Okay? So please remember this, because you know I'm using you as the union of every person in my audience when I presented second gradient theories objecting something. So I answer to you, to all objections, because I know that you belong to a school in Berkeley where second gradient variational principles and second gradient theory are unconsciously transmitted to the students, and they pretend they are perfectly following the religion of Trussell for avoiding wars. Okay, so it is like the Jewish who were officially Catholic, they they were converted into Catholic religion, but secretly they were following the Jewish religious rules. Okay, so we must go out and fight our war openly. Okay, so now how Cauchy is proving that Tn depends linearly. Of course, yesterday I wrote something wrong because here I had to write n dot E alpha for having a linear combination. So I was clearly tired. So it is good that we are revising this. Okay. So, which is the reasoning by Cauchy? He writes the balance of force for every tetrahedron having height epsilon. So the distance between this point and this normal, this face normal to n is epsilon. I write balance of force for this tetrahedron. Okay. The only clean way for doing it, Erden, is using the principle of virtual work. So I will send you my Italian text about this. Okay. And assuming that there are no edge forces on the edges, and here you have many edges, okay, he proves linearity. So that Tn depends on Te alpha, where E alpha are the three directions of the coordinate systems, with a linear combination given by n dot E alpha. Okay. So this is what he writes, and here I repeated my mistake. So Ex dot n, Ey dot n, E zeta dot n, obviously. Okay. Now, this equality is false for second gradient materials because the tetrahedron argument is not correct, as edge forces, edge contact forces are missing. Okay. How Cauchy followers state that there are no edge forces? They claim that this assumption is driven by experience. Okay, so I want to underline for you this point. Cauchy takes a body. You know, many engineers claim that this is much easier to understand than the principle of virtual work. Now, think coldly about what these people are doing. They have a body, okay? They have a body. Then they perform a Cauchy cut with a surface sigma. And then they are crazy enough to say, imagine to cut this and to remove one part of the body. Here, on the surface, which now you have out, emerging after this imaginary cut, you have forces per unit area, whose effect on the remaining part of the body is exactly the same as the effect of the removed part of the body. For them, this is clear. For them, this is physically understandable. Because Erden, you know, when you measure the state of stress of a beam, you go there, you cut the beam, and you measure the force per unit area on the emerging phase. You are doing it every day. You know, you do this frequently. This is totally crazy. Okay, this is an a posteriori interpretation of the results obtained applying the principle of virtual work. And this is not my conjecture. This is written in the books available in every library. Piola in 1822, before Cauchy, introduced the concept of stress. Actually, he cites Lagrange in the last pages of the last edition of the book by Lagrange. Lagrange introduces this concept. Okay? Then Cauchy reinterpreted, in the case of first gradient, this concept in the way in which they are teaching us, which is not wrong, but it is not the true way in which this original model has been invented. Okay, and as we want to learn how to invent new models, this historical observation is very important. Okay? So, Erden, we must write at least one paper on this, if not more than one. Okay? Because this interpretation is original. By the way, we will add some original ingredients from second gradient theories also, so this is not bad. Okay. Now, before we end, we have only 10 minutes, but we have the last lecture next Thursday. In our integration by parts, we have a completely new term. We have a surface integral of something which it is useless to reproduce now. This depends always on dw over dFi BA, the gradient of f. Okay. We have a work which depends on integral on the boundary of C star of something times the normal derivative of delta Ki. Okay? So you have a work. Okay, this is not very good. This. Let us write it delta E def. So you have a part of the first variation of energy, which depends on the normal gradient of delta Ki. Okay. So what I want to remind you is a reasoning which we already did. This reasoning is due to Euler. You have a rigid body. Okay? This rigid body is translating with the speed, with the velocity v omega, and then it has a angular velocity omega. So the virtual displacement of this is v0 delta t plus omega delta t vector x minus x0. This is, we started our course with this and we will end with this. This is the virtual rigid displacement, virtual, so infinitesimal virtual displacement formula. Then you have here applied every kind of forces. Okay. And you write, these forces can be volumic, you can have them on surface and so on. What is the work done by F on the virtual displacement? It is the integral on the body, on the actual configuration of the body, of dF, the density of force. So dF is a density, a volumic density, times the volume, or a surface density times the area, or a line density times the L, or a number of concentrated forces. So this is a symbolic way for meaning every kind of applicable forces to your body, dot V0 dt, which we can call delta U0, plus delta theta vector x minus x0. Okay? Or if you prefer, you remember, and now it is important, the skew symmetric W applied to x minus x0. Okay? You remember, W of a vector is equal to the vector W vector V. Okay? Try to go to the first lectures where we have done this at the beginning. Okay? Now, what you prove, it is rather easy, is that integral over C of dF dot delta U0 plus integral over C of x minus x0 vector dF dot delta theta. Okay? So the work done by a system of forces on a rigid displacement is given by the resultant force, inner product delta U0, plus the resultant moment with respect to the pole O dot delta theta. Okay? Now, look here. Better, look here. What is the gradient? The gradient of delta K? This is a constant, so its gradient is 0. And if you remember this expression, which is equivalent, this one, it is W. So the gradient of delta K is the skew symmetric tensor representing rotation. Okay? Now, when Euler wanted to study beams, and he discovered that in his integration by parts, something was expending power or work on rotations, he said, here I have a moment of forces. Okay? Now, what we will do in the last lecture, we will study the power or the work expended in this virtual displacement. Delta K equal delta U0 plus W x minus x0 plus U x minus x0, where U is symmetric and W is skew symmetric. Okay? So that we will be able to give a mechanical interpretation generalizing Euler's interpretation also for this expression for work. So we will understand that this animal here is a double force, and we will understand what is a double force. Okay? Okay, so I think we can stop here. Okay, Alessandro. Alessandro?
Eccomi.
Ha chiuso?
Sì, scusate, ero al telefono.